Um, thanks, Olga. Thanks everyone for being here. Thanks for the invitation. I'm very happy to share this work with you and to get some, discussion going on because I mean sometimes as researchers we do a lot of work, but it feels a bit distant from other topics or people who are interested in the stuff. But I believe this could be interesting to many, not just those who reviewed the paper and found it interesting, not just those who were at the presentation at the conference, but many others. So I hope you will find this interesting and maybe you will be able to use it for your own research or future application. So my talk today is gonna be focusing on retraining language models, large or small, whatever they are, in federated or low bandwidth environments. That's what we've been doing in Cambridge in our machine learning systems group for the past for the past year. So the outline is this. I will introduce federated learning because maybe you are all familiar with it, but I really want to give our point of view and the way we saw federated learning for this particular task. I will also have a couple of slides related to pre-training because I think it's useful to set the stage and say what are the basic ingredients for those who are not super familiar with them or who have never trained LLMs from scratch. And then I will discuss this Photon system. That is the paper you hopefully have read before this meeting started. If we have enough time, I would like to touch on the depth method, which is another paper that was accepted at ICLR 2025. And then I will wrap up and we can start discussing things. Of course, you can ask me questions. I think I will leave enough time at the end for having a longer discussion. But if there's something that is really unclear and you want me to explain it better, feel free to stop me if you can. As Olga said, yes, I've studied in Bologna for 5 years, bachelor and master's in physics, and then I moved to Cambridge for my PhD. I met Nick Lane, who was starting his new group in Cambridge about federated learning. I was interested in federated learning was my topic for my master's thesis, and I was actually the third user of Flower, historically speaking. So that's why, I mean, I got super excited about it since the very beginning, and then. I mean, it was just a matter of time for starting collaborating with people, with folks here. Now I'm a third year PhD student. I'm currently also an intern in Flower Labs as a research scientist. And we have this super new website about flower research if you want to check it out. Of course, we have a website of the research group in Cambridge as well. So with this, I will start by introducing federated learning. And this is going to last just a few minutes. And the most important bit I want you to focus on is first, of course, the definition and what are the components involved, but also the second part of this introduction, which is going to try to bridge the gap between what's a standard distributed training setting and what federated learning is, and how we think about this stuff these days. So federated learning is very well defined now. I think if you have run into these advances in open problems in federated learning paper, it's actually a book. It's like 100 pages. Now they have a super new and super well-defined definition that I've reported here. And what's most interesting is that they clearly wanted to, with this new version, they clearly wanted to define a few things that were maybe unclear and that were misinterpreted by even the research community at the very early stages of federated learning. So what is it? It's a machine learning setting. We have multiple entities collaborating together. We call these entities clients, and they want to solve a single, like unique or a collaborative machine learning problem. And they work under the coordination of a central server or service provider. It's not like we call it parameter server because it might just send, training instruction and just coordinate what these clients need to do. It doesn't need to hold the parameter itself. And how does this work? Well, each client's raw training data, it's stored locally and it's in most cases private. And it's never exchanged, not with the server, not with the other clients. And this is the peculiar privacy-preserving part of federated learning. Then this client, what do? They use focus updates that are intended for immediate aggregation across all of them. And these would help achieve the learning objective. What you can see on these on the right-hand side of the slide is the original algorithm, the original paper proposed. And you can see that there's these training rounds, we sample clients, we do some training stuff, we aggregate these training results, and these repeats until convergence. So now it's pretty simple. But what's interesting to us, and what was interesting to us when we started looking into pre-training, was what's the difference between this paradigm and what's the standard distributed training algorithm. Here you have this slide with this maybe two quick animation about distributed data parallelism, which is basically the most well straightforward, I would say, distributed algorithm you can apply when you do large scale training. And what happens here? Well, we have a centralized data set, right? In this center, we sample batches from it. Each of these batches split it into smaller pieces we can share with our compute units that can be GPUs or entire servers. These workers, these data parallel workers, compute the partial gradients onto this part of the batch, and then they synchronize over usually a ring topology all these gradients to have the estimate of the full gradient of the batch. At the end of the synchronization, every data parallel worker has the full gradients and can perform the optimization procedure, which usually is just a set of summation or multiplication. For example, in the case of LLM pre-training, we use EMW, and then we compute this first and second momentum, and these compose with the learning rate, the update that we apply to the model. And this procedure is, of course, repeated over and over again until we reach the convergence. Now, if we take the same perspective and we apply to federated learning, what does it happen? So we have a number of workers, but these are clients now, and they own the data, right? So instead of having a centralized server with the data is already distributed, and we can't choose anything about that. What we can choose just the amount of sample composing a local batch for these clients that every round receive the current version of the model parameters. They do some local training, a few steps usually. With these few steps, they compute gradients and apply them without requiring any synchronization with all the other clients. And after these few steps, each client has a new version of the model. And that's when we synchronize. So each client has this new version of the model. We send it back to the server, a parameter server in this case, and the parameter server synchronizes these different versions of the model. Of course, this procedure can use different type of optimizers. Maybe you have heard of adopt, that is, I think, the most general the most general algorithm where you can basically choose any kind of adaptive optimizer locally as well as on the server side to aggregate these model updates. But most importantly, we need to, I want you to understand that what happens on the clients is an application of gradients without synchronization. So the model locally moves in this lost landscape, and then it's synchronizing frequently. Now, if we now look at the two algorithms together, we can spot a few of the differences, even though they may look very similar. So what are these differences? We have workers on the DDP side and clients on the FL side. We have a partition data set on the DDP side, but this is due to the batching system and the random sampling that we have there. And now these are distributed across workers. Instead, for the FL case, what we have is the distributed by nature dataset, the federated dataset that we have. And in most cases, this creates issues because data may be heterogeneous, and we can't usually control how heterogeneous they are or how this heterogeneity affects the training procedure. On the left-hand side, we have the ring reduced to synchronize gradients. And because of this, we always have a single model representation. And this is very important. So at all times, the model is always one. Even though it's distributed, it's copied onto all the workers, it's always one. What we have is multiple gradient representations that are then synchronized in order to form the full batch, but the model representation is always one. Instead of the right-hand side, we have multiple optimizer, a local one, a server one, because we have multiple versions of the model as well. The server does have a model that serves as let's say a checkpoint that is kept constantly updated in order to make sure that the training can progress and we can at least control whether the training is converging or not. But also clients have their own model because they start with the same model at the beginning of the round, but then they apply the local steps, which means that the model moves. And before the synchronization, each client has its own model. So we have multiple model representations. Now, importantly, what else do we have? We have that the federated learning is much more communication efficient compared to distributed data parallel. And the reason why is that is because since we are applying these local steps and we are synchronizing across clients less frequently, basically we don't need to communicate every local step, which is something that DDP requires. So we apply some local steps. Let's say that our training lasts for 1,000 steps. 1,000 times we need to communicate for DDP. But for federated learning, in most cases, applying local steps, we can reduce this cost, maybe by synchronizing every 10 steps. And this produces a 10x reduction in communication costs. Now, I will now move to to explaining a task that is relevant to this presentation, and it's one of those where DDP, distributed data parallelism, it's critically important. And this is, of course, the pre-training of language models. So what I will explain here, just the ingredients, the basics about it, and why DDP, of course, is relevant here. But you may see some similarities with other tasks. I mean, maybe you know it already. And what's important to know is that most things I will mention and most things you will see that this task shares with others are probably relevant to our federated work as well. So even though our Photon system and other things that we've done in the past like a year or so have been focusing on federated LLM training, in most cases there are things that we can transfer to other tasks in order to improve their efficiency and so on and so forth. But of course, we can discuss this later in case you are interested. Now, what's LLM pre-training and what are the machine learning needs of LLM pre-training? Well, usually you start with model architecture. So you choose whatever is available, or if you want to reproduce experiments, or if you want to beat, I don't know, some baseline or so. In most cases, I mean, in recent days, what happens is that we choose the decoder-only architecture, which is autoregressive. And because of this, we can, this is the most, let's say, parameter efficient, excluding sparse model architectures such as mixture of experts. And on top of this, we need to choose the data set, the training data that we use. The better the training data, the better is going to be the model in most cases. So what we care about is the quality, how well curated it is, where it comes from. But in like 100% of the case, this data comes from the web. So it's been web scraped, maybe filtered, or cherry picked in order to, put together the best mixture of, I don't know, academic data, code data, or other kind of data sources. Once we have composed the dataset, we also need to choose how to mix it or how to feed the model with it. And you can see on the right-hand side, there's on the top right of the slide, there's a figure I taken from the small LM2 technical report from Hugging Face. And what's very interesting is that they basically choose several stages of the training and they mix the data differently depending on the stage. Of course, here they had a lot of bandwidth, right? Like a lot of possibilities because they wanted to train up to 11 trillions of tokens, which is really, really a lot for the model size they trained. And but you can see how they mixed different type of data sources, and this mixture is super important to achieve a good pre-training performance. On top of this, we need an optimizer. We need an optimization procedure. Usually people go for ADAMW, so we Tube Menta, very good optimizer, very stable usually. if it's well conditioned. And that's also why people also use learning rate schedulers. They use learning rate schedulers to better condition optimization and to make sure that there are no little like fluctuations in the optimization, no gradients blowing up, activation exploding, these sort of things that are very common when we train models that are super, super big, like in the billion scale or 100 billion scale. Of course, this is not enough. Why this is not enough? Because the workload for pre-training LLMs is massive. It's massive because of the data, because of the number of parameters we have to train, because of yeah, and many other aspects of, for example, how to control this training, how to check whether it's training what we need or not. Because of this, people usually deploy this into a distributed environment using several GPUs, and they need a distributed algorithm to do so, to better understand how to distribute the workload. And that's why we also need to talk about the training infrastructure. Training infrastructure is composed by entering the data, the training data. So how do we take this big data set? How do we partition it? How do we feed the GPUs with it? And then how many GPUs we need and how to make them effective and efficient. And usually this is mostly related to networking solution to make the connection between GPUs very, very quick so that we can consider a big data center as if it's a big GPU, right? So in this context, we started thinking about federated learning to solve some of the challenges or to mitigate some of the issues that pre-training usually has. This project was a collaboration between Flower Labs and the Machine Learning System Group in Cambridge. And we also had the help of some visiting students from BUPT and Zhejiang University. Now, why did we try to use federated learning for this stuff? Well, we were starting to focus on three major issues that LLM pre-training faces when we want to scale it up, to scale the workload up to, I don't know, bigger models or bigger data sets and so on. The first was sourcing the compute. So you need more compute if you want to train a bigger model. And the sheer computing infrastructure needed nowadays is very critical because people now, if they want to train a bigger model compared to what they did before, imagine you are Meta and you want to train an even bigger model compared to the Llama 4 that came out recently, then you need to build a new data center because the compute you have in a single one is not enough. You need more. Of course, scaling the data center construction, it's sometimes very always all the times very expensive, but sometimes also impractical. So what we wonder is whether we can use the existing compute infrastructures that are already available, like GPUs in the wild. We can scale out and use the internet as our training infrastructure. Of course, federated learning allows for this because there the bottleneck would be the communication, the network, the interconnects between the center. And we know federated learning is much more communication efficient compared to data parallel. Another aspect is the robustness. So all these training pipelines, all the software stacks are based on maybe like if you're using NVIDIA GPUs, NCCL and all these on these directives, but they're mostly based on collective communications protocols. What's the problem with this? Well, nothing, but if you work on a very extensive training infrastructure, what happens is that any kind of failure you experience, network failure, GPU failure, any kind of hardware failure, and in the Llama 3 report, you can see that they experienced the 78% of the interruptions they had training Llama 3 were due to hardware, which is something you usually cannot really control. And whenever you have one of such failures, you need to stop everything and restart from a checkpoint. And this is usually very expensive because it can take hours, 1, 2, 3, 4 hours. And this is due to the single program multiple data design that these software stacks adopt. In this case, federated learning could help because training happens in isolation. Each client has its own little training infrastructure. The training goes applying the gradients, and the orchestrator, if one client fails, can decide to resume it or go on without its updates, because this is even possible. And this doesn't require anything to stop. It may be less less data efficient in a way because we wasted a part of the update, but it doesn't require any kind of resumption, very expensive resumption procedure. The third component I want to mention is related to data. These days, it's quite a controversial claim, the one that I'm trying to make here, because of several reasons that we can discuss maybe later. But basically, what was interesting to us was this paper from Villalobos that was predicting back then that, and I think it's still relevant, that we will run out of publicly available text data by next year meaning 2026. What's the problem with this? The problem is that we will not be able to scale the training data sets as we were doing before if we want to get models that are bigger. So we will hit the wall, the famous or infamous wall of data. Of course, federated learning can help with this. Why is that so? Because federated learning can tap into private data sources, and these private data sources will likely continue to produce data continuously. Problem with this is that they are private, and the problem with private data is that there are a lot of regulations on top of it. But federated learning, being private by design in this sense, can certainly help with this. Now, we were not the only one to be interested in this field. There were like a lot of works around federated pre-training, maybe more distributed low communication. You can see papers from Google. Dataset Grouper was probably the first. Then there's a series of papers from DeepMind under the name DiLoCo, and even the industry with some startups, Flower Labs as well, Prime Intellect News Research. We started looking into these kind of solutions and proposing new applications or reproducing some of the previous results. In this setting, we've developed Photon. Photon is probably the first system, no, definitely the first full federated system for LLM pre-training that you can deploy. It's built on top of Flower and PyTorch. So compared to Flower, that is completely machine learning framework agnostic, our Photon system is still in the research phase, relies onto PyTorch. And we demonstrated that we can train billion scale models across distributed data and compute as well. We showed that it's scalable, it's efficient, it saves communication costs, but still retains model quality, which is the most important thing you care about when you spend a lot of money on a large language model. We also assess the capability of Photon to cope with node failures, which is something that is very common even in a single data center level. And we can see how the federated learning paradigm can solve some of these issues by just being able to continue the optimization even though one node fails. A big result I'm really proud of is this 13 billion parameter model. This, of course, is massive. We needed a data center, 32 GPUs to collaborate with each other in order to train a model of this size. We followed new training recipes from Hugging Face, as well as a new optimizer we started developing a few months ago. Now it's on archive if you want to check it out. What was very interesting for system people in particular here is that by taking advantage of the lower communication costs of federated learning, we are able also to increase the local throughput of clients. And here the result is impressive because the throughput we observed is 2x compared to centralized. And this is just due to the slowdowns that centralized has in environments with a bandwidth that is not like the InfiniBand, the bandwidth with like terabits per second. If we talk about scalability of Photon, what we try to do is training different model sizes with different training infrastructures. And the benefits we saw for big models also for small ones. Of course, these benefits depend on the bandwidth that we have across nodes. The lower the bandwidth, the more the benefit, because centralized solution is going to be even slower. But also we observe again a better utilization of the compute, because we don't need to stop. We don't need to stop for the synchronization to happen, and we can heat data locally more and more again. And as a result, federated learning or federated learning optimizers can use more tokens in a better way compared to the standard ones. Another aspect we were interested in was that of the robustness. As I said, single node failures are pretty common. And what happens here, and what you can see in the yellow, orange yellow line at the bottom is that at some point one year, I think it was two or something, two clients failed for that particular round. So we had a spike in the perplexity, but this didn't break the training. And notably, we didn't have to stop. We didn't have to stop the training pipeline or anything like that. We just needed to forget about those two clients for a second and then take them back when they solve their hardware or whatever issues they have. It didn't impact the training convergence, which is super interesting. Of course, there's a temporary spike into the loss, but it doesn't impact the model quality later on, which is most important. So why does this work well? There are many reasons, of course, some of which may be already clear, others a little bit hidden behind these various components. From the system perspective, having a central orchestrator is very useful because it allows you to basically cope with any kind of failures of this kind. And I was happy to hear from a person working at Meta on the PyTorch ecosystem that they are working towards this kind of direction as well. So we'll probably see a switch towards a centrally orchestrated kind of distribution, even for PyTorch, for the native PyTorch. It works well because it allows for heterogeneous compute to be used, because we don't care about whatever clients they have, whatever resources clients have. Of course, what we care about is that they can hold the full model locally. What they may be differ on is the amount of samples they train for a given round. And these also allowed us to scale the compute available much better. The centralized needs to stop the training, reconfigure the parallelization configuration, and then redeploy the runtime. Instead, for federated learning, we just need to get a new client into the federation and let it train on its own data and aggregate its updates. As for the machine learning part, the federated the components that make this work well are, again, several. There's a federated denoising, so we're able to stabilize all these pseudo gradient updates that we receive from the clients, which are usually super critical. If just one of the little partial batch updates that we have in centralized that basically blows up because of some activations exploding or something like this, it's very difficult to recover from it. And that's why people use gradient clipping or sort of techniques. Here for federated learning, we have a stronger denoising effect due to the fact that we are applying local updates and we are averaging whatever happened in the last 100 rounds or so. And this also allows us to use higher learning rates locally compared to what you could do in centralized. So what we observed is that basically when you decrease the batch size, you would like to use a lower learning rate, a smaller learning rate. This because smaller the batch size, the noisier is the update. In federated learning, we could increase the learning rate much more compared to what you can do in centralized safely without letting the model explode. Of course, on top of this, there's the entire discussion about handling data heterogeneity, but we demonstrated that you can have heterogeneous data sources. In that case, we took, I think, the pile and in its components, and we distributed the components of the pile, and we trained on this distribution. And this worked pretty well. I want to mention two potential benefits of using federated learning technology. On the system side, we have that of workload placement. So if we have an orchestrator that schedules some workload because it has the full control over the model training, it can choose, for example, okay, now I have a big workload to do. I'm going to sample those clients that are more that have more resources. Or now, for example, I want to spend less money on this particular training step. So I'm going to sample those clients for which the energy or the infrastructure costs less. Or maybe I really care about the environmental impact of these training pipelines, which we should all really care about this stuff, but sometimes is a bit confused or difficult to understand what's going on. Well, if I have the control over this stuff, I can say, look, now I want to use this particular data center that is greener because it's using a greener energy source. On the machine learning perspective, instead, we have the personalization aspect. A thing that is very critical for federated learning runtimes is that of handling the heterogeneity, yes, but in most cases, you do want to get a full, a global, a single model, a single model trained, a single training objective. But sometimes after a while, after you've trained the model for quite a long time, you may want to start to personalize and to get to something that is better at performing for the local client. Of course, here we go towards the direction of understanding how to serve this kind of model, how to do inference for this infrastructure, which is another topic we didn't cover. But of course, federated learning can help better compared to centralized, where you really don't know. You have trained the model onto this data mixture, but you really don't know what would be the best personalization or the best subset of the data to personalize them. Okay, now I would like to briefly mention the depth paper because it's still a little time. For the depth paper, what we did was going further towards further into the federated problems that we may face when we scale these training pipelines. So basically what we started asking ourselves was, what would be the challenge of really sourcing compute as well as data from different places on the planet, right? Data can be really diverse. We can have different languages because maybe, I don't know, we source data from the UK and we get a lot of English. We source data from Italy, we get a lot of Italian, maybe some English as well. We source data from Singapore, where I've been recently, and you will get a lot of Chinese data as well as English data. So you will get both. So how do you deal with this? And how do you deal with heterogeneity in the domains? For example, maybe our research group has a lot of text data regarding machine learning systems, and maybe you go to another group down in the city center in Cambridge and they do literature, they do humanistic studies, and they have completely different data. They don't have code at all, or this sort of thing. So how do we deal with these kind of problems? The problems usually comes to the embedding layer and the tokenizer, because these solutions, the tokenizer you may choose may not be super effective at compressing the information of a particular data source. And there's a lot of research in the NLP community in order to get the best tokenizers and the best embedding layers, because these are very critical to perform the machine learning task itself, right? So without going too much into the details, the problem is sharing vocabularies, sharing tokenizer, and sharing these embedding layers. But these are a separate component compared to the transformer body and the transformer blocks that we're training, right? So our idea was then of separating these two training, the training of these two components in order to personalize or make things more efficient depending on the training infrastructure that we had at the time. That has several methods. It can and has several contributions. It can enable the vocabulary agnostic training of these models, because we can personalize everything locally. We can say, look, you client, you can train your own data set, train your own tokenizer, have your own vocabulary, and have your own embedding layer, but still operate on the same transformer body as everybody else. And because of this, it also reduces the communication and the memory footprint, because instead of having to communicate a full model, we can keep private the embedding layer, for example, and just communicate the transformer body. Of course, these are not super savings when it comes to large models, but when it comes to small models, the embedding layer is usually a big chunk of it. What we noticed as well was that using these federated learning technologies, as well as the capabilities of personalizing the vocabulary, transformer bodies can be much better than the centrally trained ones. This is because they have more focused updates and they learn how to adapt to different data distributions better. And this was very easy to spot when we started doing experiments over adaptation phases. For example, when you hear about data annealing or these sort of things. So whenever you have a model that works already well on something and you want to adapt it to a particular domain or data source in general, you do that annealing phase where you basically feed the model with specific domain-specific data, and you want it to be fine-tuned over it. Of course, you're still doing language modeling, and what you can use to benchmark the effectiveness of this transformer body is looking at the evaluation perplexity, for example, as well as downstream tasks that are specific to that domain or data source. If you look at the paper, you will see a lot of diagrams of this kind. These are two of the methods we propose. On top of we have trim, where basically the embedding layer is trimmed from, we trim from the embedding layer those part of the vocabulary that particular data source does not use, which means that, for example, if you have a Chinese data, and you don't need all the tokens related to some maybe English or Italian words, and then there's no need for them to be trained, right? So we can take it out, save a lot of memory locally, as well as in communication costs, because we don't need to share the full embedding matrix. Specking standard is the method at the bottom. It's even more personalized because here every data source has its own vocabulary, its own tokenizer, and its own embedding layer. And what it's exchanged, and you can see in the middle, step 4 and 6, it's only the transformer body. And of course, what happens on the server, on the parameter server, the orchestrator here is that we only average the transformer body across these data sources. And even though they are very personalized in the way they compress their text data, still the transformer body can learn and actually can adapt much better than centralized. What we observe is the reduction in communication costs. That is very impressive. And memory footprint, of course, this depends on the model architecture that you adopt. Notably, these methods all converge smoothly, despite being so different in the way they learn from the data they observe. And the downstream task performance are very promising because we can improve and other centralized training pipelines, mostly those for which you don't need to super fine-tune the way you use the data mixture. For example, we used as baselines data mixture where we're treating all data sources uniformly or sampling proportionally to their to the amounts of data that each of these data sources have. So with this, I go to my final slides. Of course, there's many interesting future direction we are currently interested in. For example, there's still a big convergence gap between centralized and federated when it comes to compare on a ISO token basis. So whenever we train these two solutions with the same amount of tokens, most likely the federated one is gonna perform slightly worse. What I'm currently at this time doing is training a fairly big model, 1B or so, on a very big data set. So for a long training duration. And what I'm starting to observe is that if the training takes longer, the performance gap is going to be smaller and smaller. And I actually have one training run where the centralized perform worse. But I still have to run all the downstream and all the assessment to make this bigger claim. There's a problem of flexibility and inclusivity. I mentioned that these clients need to hold the full model. But what if you don't have enough resources to hold the full model? What can we do? So these are still an open question. An open question is, what do we do in the ultra efficient environments? Because I said that the communication savings are always there, right? Because they're due to the local updates happening on the federations. So can we apply the same idea inside the data center where you need to do ultra efficient training pipelines? Of course we can, but the Photon system, for example, is still a research framework. So it's not meant to do super ultra efficient training runtimes. So what are the gaps that we need to bridge there? Do we need to change the backend? Do we need to implement some compression? This is still an open system research question. As for the broader picture, if we want these methods to be adopted like worldwide, we will need to develop a rewarding mechanism to make sure that a big contributor is going to receive something back from using resources to train these models, and we will need to make sure that these can be accounted for. So these are the bigger picture, bigger questions that we'll need to answer before these methods are going to be are going to spread worldwide. Okay, this is my last slide. I just want to thank all the members of our team that have been super helpful in doing this research. There are too many faces here, but I really wanted them to be somewhere so you can see them and you can spot some names. Maybe you know some of them. And yeah, with this, that's the end of the talk. Thanks a lot for listening. I hope you liked it, and I'm happy to answer any question and to have a discussion with you.